Welcome to the deep dive. Today we're jumping into the online encyclopedia of integer sequences, the OEIS. It's this amazing database for number patterns. We're looking at a sequence that's particularly interesting for number theory students, A000324. Now, this isn't just some random list of numbers. It's defined by a nonlinear recurrence. Starts A01, A1, E4. And then for any term after that, n greater than 1, you calculate it as an1 squared minus 4 times an1 plus 4. What grabs you right away is how fast it grows. You get 1, 5, 9, 49, then boom, 2209. It just rockets up. But, underneath that speed, mathematicians have found some really stunning connections. So our mission today is to kind of unpack those surprises. What makes this one so special?
Indeed. It's a perfect example, really, of how a rule that looks pretty simple on the surface can actually hide some quite profound mathematical structures. For you, diving into number theory, finding these layers, that's where the real excitement is. And one of the first really insightful things here is that A000324, it's an infinite coprime sequence.
Coprime, meaning
any two different terms you pick from the sequence, they don't share any common factors other than one. They're relatively prime.
Wow.
And this isn't just, a neat party trick. It's a pretty rare property and quite significant in number theory. Often links to big questions about primes, it suggests there's this deep order hiding in what looks like, chaotic growth. Michael Somos first pointed this out.
An infinite coprime sequence from that simple quadratic rule. That's genuinely remarkable. So when you find something that elegant, does it often sort of hint that it connects to bigger ideas, maybe part of a larger mathematical family?
Absolutely. You've hit on something key there. If you look at the bigger picture, A000324 is actually a special case. It fits into this broader family of sequences known for having what are called exact mutual K-residues. It's the case where K equals 4.
Okay, K-residues. Can you break that down a bit?
Sure. So basically, each new term in these sequences is the very smallest number you can find. That's bigger than the previous term. A and D leaves the same remainder, K, when you divide it by all the terms that came before it.
Ah, I see.
Our sequence, A000324, it follows that exact pattern for K4. The general setup is pretty neat. A1 is K plus 1, and AN is the minimum MAN1, such that M mod AI equals K, or all I before N. And this family, it's got some famous members like Sylvester's sequence, that's A000058, happens when K1. And even the Fermat numbers, A000215, they fit in there for K2.
So it's not an outlier. It's got this distinguished lineage. That adds a whole layer of context. That's incredible. Okay, so besides the recurrence in this family connection, are there other ways to write down A00000032, maybe more explicit formulas?
Yes. And here's where it gets really interesting, I think. This sequence connects directly to the Lucas numbers. That's A00000032.
Exactly this. Well, for our sequence, A00000324, it turns out that for n greater than 0, an is just the 2 to the nth Lucas number plus 2. So an equals 2n plus
2. Wow. Yeah. And there's even another way to put it. For n greater than 1 an is the square of the 2 to the n1th Lucas number. So an, L2, n is 1, 2.
That's amazing.
These explicit formulas, they're really valuable because they show this beautiful structure that you just don't see immediately from that quadratic recurrence. It connects A000324 right into the heart of well-known number sequences.
It really is like peeling back layers, isn't it? Finding something more fundamental underneath. Now, I also saw some notes about sums involving A000324. How do these terms feature in, say, mathematical identities or series?
Right. Good point. There are some elegant identities. One that really stands out, highlighted by researchers like Jennings and DeVerney, is this summation. If you sum the terms 4n divided by an, starting from n1 and going on forever, so sum n1 for nan, it actually equals exactly 4.
The whole infinite sum just equals 4.
Exactly 4. And, this isn't just a numerical coincidence. Results like this show how deeply the sequence is integrated into, mathematical analysis, connections beyond just integer sequences themselves. It reveals a sort of hidden harmony.
Okay, so let's recap. We started with this fast-growing sequence from a simple recurrence. Then found out it's an infinite coprime sequence linked directly to the Lucas numbers.
Right.
And it's part of this bigger family, including Sylvester's sequence and Fermat numbers. This deep dive into A000324, it really shows how much richness can be packed into just a few numbers and a simple rule. So for you listening, maybe grappling with number theory, what's the big takeaway here?
Well, I think it poses a really important question, doesn't it? What other sequences in the OEIS, maybe ones that look easy because they're defined by simple rules, what other ones might be holding equally complex, equally interconnected secrets, just waiting for curious minds like yours to uncover them.
Yeah.
It really reminds us that sometimes the most intriguing mathematical landscapes, well, they're found in the most unexpected places. It challenges our whole idea of what's simple and what's complex.